A comet from another star is hurtling toward Mars, and Michio Kaku just raised the alarm. New data shows 3I Atlas could pass closer than any interstellar object in history. The risk, a collision that could devastate Mars orbiters, rovers, and reshape its atmosphere. This isn't science fiction, it's happening now. The new alarm bell data breaks the calm. It started with a number, a decimal place that refused to stay still. On a quiet July evening in Cambridge, a Harvard research server completed its latest orbital calculation for 3I Phi, the interstellar comet discovered earlier this summer. The resulting path plotted against Mars's orbit showed something few expected. The approach distance had dropped significantly. At first, no one panicked. Orbital models shift all the time as fresh observations feed into the system. But this shift was different. The margin of error wasn't just smaller, it was collapsing fast. Within days, simulations showed the comet's trajectory tightening within a range closer than Phobos, the innermost moon of Mars. That's when Michio Kaku stepped in. Known for his deep understanding of both physics and public communication, Kaku reviewed the new orbital data and saw a pattern forming. This wasn't just a wild comet passing through. It was on a path that might bring it uncomfortably close to a planet where we've already planted scientific assets and pinned future human plans. Mars was now in the conversation, not just as a backdrop but as a potential target. The real concern wasn't that a collision was imminent. Statistically, even the updated simulations still leaned toward a flyby, but the uncertainty band or orbital ellipse had shrunk from millions of kilometers to less than the width of the continental United States. At this range, a small outburst, an unpredictable gas eruption from the comet's surface, could be enough to push it from a safe pass to a high-speed impact. With each new observation from telescopes like JWST, VLT, and Hubble, the data refined itself, and not in the direction anyone hoped. The comet's projected corridor remained inside a zone that planetary defense teams call the scrutiny threshold, a range close enough to justify active monitoring, even if the risk remains technically low. Internal messages bounced between observatories. Some astronomers used words like unnerving. Others, less publicly, said they were watching for what they called the pivot, the moment when the data finally tips toward a confirmed threat. That moment hadn't arrived, but it wasn't far off either. Kaku made the decision to go public. He issued a warning, not to stoke panic, but to wake the public and policy leaders to the new reality of interstellar threats. For the first time in planetary defense history, the object in question wasn't native to our solar system. It was something born in a different sun's gravity, drifting for untold ages before crossing paths with us now. The cosmos doesn't care about our borders, Kaku said, and the solar system isn't just Earth's domain anymore. If we're building a second home on Mars, we'd better learn to defend it too. His warning triggered a ripple through space agencies. NASA confirmed it was reviewing Harvard's models. The Jet Propulsion Laboratory reallocated computing power to run fresh simulations. The Planetary Defense Coordination Office started issuing quiet updates through internal networks. Something had changed. What started as a routine detection had become a full-scale alert. The comet was real, the data was solid, and the clock was ticking. But to understand what was truly at stake, we had to look deeper at what this object actually is and why it behaves in ways that break our usual models. Don't forget to subscribe for more breaking space news and deep dive explanations like this. Object Profile. What is 3I Atlas really like? To understand the danger of 3IA, you first have to understand what it is and what it's not. This isn't just another frozen relic from the Kuiper Belt. It's a visitor from another star, a body whose speed, angle, and chemistry mark it as truly interstellar. Detected on July 1, 2025 by the Atlas survey in Chile, it was quickly flagged due to its hyperbolic trajectory, a path that means it's not orbiting the Sun, but merely passing through. From the start, it moved differently. Its excess velocity, the speed after escaping the Sun's gravity, was measured at over 58 kilometers. Its eccentricity was more than 6, far beyond any solar system comet. That alone placed it in the same category as Oumuamua and 2I Borisov. But 3IA wasn't just fast, it was active. Unlike Oumuamua, which showed no outgassing, 3IA revealed a bright coma and a distinct tail, Observations from the Gemini Observatory, the Very Large Telescope, and space-based platforms like JWST revealed an unusual chemical signature, high levels of carbon dioxide, organic molecules, and volatile gases not normally seen in comets from our own system. But there was more. The orientation of its path, retrograde and sharply inclined, meant it was crossing Mars's orbital plane at a steep angle. The timing couldn't be worse. The comet would make its closest approach around early October, just as Mars passed near the same region of space. This raised a new issue: orbital alignment. 3I Atlas wasn't aiming for Mars intentionally, but physics doesn't require intent. Visibility added another layer of complication. For large parts of its journey, the comet remained in a poor solar elongation angle, making it difficult to observe from Earth. Only high-powered instruments, and often those based in orbit, could track it clearly. That meant fewer data points, wider uncertainty, and a delay in calculating risk. Despite all this, what fascinated scientists most wasn't just its origin. It was its behavior. 3I Atlas didn't vent gas randomly like most comets. It pulsed at near regular intervals. These 17-minute cycles of outgassing, visible in brightness spikes and chemical shifts, suggested a process that was somehow regulated. No other known comet does this. It raised the possibility that internal resonance, or perhaps rotational heating, was causing rhythmic eruptions. But for some, including Kaku, the regularity was unsettling. Nature can be chaotic, he said. But when nature becomes predictable, we should ask why. And as the comet approached Mars, those pulses could act like tiny thrusters, nudging its course, however slightly, toward a far more dangerous encounter, the Mars confrontation. How close is close? By mid-September, the numbers solidified. The best-fit trajectory of 3I Atlas placed it on course to pass just 0.99 astronomical units from Mars, about 28 million kilometers. At a glance, that seems like a wide miss, but scale matters. In cosmic terms, it's a near scrape. The Moon is only 0.0025 astronomical units from Earth, and Mars's own moons, Phobos and Deimos, orbit far closer than that. So when a hypervelocity object from beyond the solar system comes within that range, it's not just notable, it's unprecedented. More concerning was the uncertainty corridor. Orbital models aren't just lines, they're zones of probability. The closer the object gets and the more we observe, the narrower that zone becomes. But for 3IA, even the most conservative simulations still showed a thin tail of possibility, brushing the edge of Mars's gravitational influence. In some runs, that tail dropped to within 50,000 kilometers of the Martian surface, closer than Deimos. Planetary defense teams at NASA and ESA began running Monte Carlo simulations, thousands of trajectory variants, each testing how different conditions could nudge the comet's path. In most outcomes, the object passed harmlessly. But in a few, especially those factoring in unpredictable outgassing events, the path bent dangerously close to Mars. This matters because Mars is no longer just a science target. It's an active outpost. Orbiters like the Mars Reconnaissance Orbiter, the Trace Gas Orbiter, and China's Tianwen-1 all rely on stable orbital paths and uninterrupted communication. If 3IA gets too close, not even a collision is required to cause disruption. A glancing tail pass, a radiation spike, or a debris trail could be enough to knock out critical systems. Even if the planet itself is spared, the infrastructure isn't immune. And with plans for future missions, including potential human landings, Mars's strategic importance is only growing. This close approach raised a new kind of alarm, not about Earth, but about our growing footprint beyond Earth. But the real wild card wasn't the distance. It was the forces acting on the comet that could change it all. Forces that could shift the path, natural versus unnatural effects. Every comet shifts slightly as it nears the Sun. The heat causes surface ice to vaporize, releasing jets of gas that push back against the nucleus. These jets can act like tiny thrusters, nudging the comet's course ever so slightly. For most comets, it's a minor drift. But 3I Atlas isn't most comets. With its hyperbolic speed and tightly modeled path, even a small adjustment could mean the difference between a safe pass and a planetary hit. The outgassing from 3I is not random. Multiple observatories have now confirmed it pulses every 17 minutes, with gas eruptions aligning to the object's direction of motion. That kind of rhythmic behavior suggests internal processes that are more structured than the chaotic venting we expect from icy bodies. The result is a measurable non-gravitational acceleration, a slow but constant deviation from purely solar-driven motion. In standard mission planning, these forces are taken into account. But in this case, the speed, angle, and rhythm introduce a layer of complexity that's harder to simulate. Every pulse acts like a small course correction, and we can't be sure what direction the next one will push.